Hi, welcome to the first video. So we're going to go over 3.4 Introduction to Logarithms. We will see how this goes. We'll see how the reception is, but this is not a replacement for lectures. So logarithms, we start off with, before in Unit 3, we talked about inverses, and we also talked about exponential functions. And exponential functions are, for example, f of x equals 2 to the x. And let's graph this real quick. F of x equals 2 to the x. With 2 to the x, I'll just make a little table right here. X and y, or y in this case is equal to 2 to the x. Let's plug in some points. We have -2, -1, 0, 1, and 2. 2 to the -2 power, a quick little reminder. If you have a value to the -2 power, that's equivalent to making it 1 over this whole thing, but with a positive exponent. So 2 squared, which is 1/4. So this would be 1 over 4, 1 over 2, 1, 2, and 4. And graphing this, we'll see we have a nice little curve that looks kind of like this. We see it really gets close to touching the x-axis, but it goes up very, very fast to infinity. So some key features about this function, our domain, we'll see which x values work. And we see every x value works. With 2 to the x, we could have negatives, I could have 0, I could have positives. There's no value that makes this undefined. So my x values are all real numbers, or -infinity to +infinity. Reminder for intervals, if we don't include it, we use parentheses, and we never use brackets with infinities. So my domain is all real numbers. Next up, my range. My range, I look over here. I see I'm going positive. I'm going all the way up. So I go to +infinity. But I get really, really close, and we'll see, do we touch 0? So let's say, for example, I see I'm getting really close to it as I go to bigger and bigger negatives. So 2 to big negative, let's say like -10. This becomes 1 over 2 to the 10. And 2 times 2 times 2 times 2, that will always be positive. So the denominator will always be positive. It'll never be 0. It'll never be negative. It'll get really, really close. Like 1 divided by a super big number, that gets really, really close, but it won't be 0. So my range in this case will be, oh, wrong one. I use parentheses, 0 to infinity. I get really, really close to 0, but I don't include 0. Next up, my y-intercepts. My y-intercept in this case, I'm touching it when x equals 0, I have 1. At 0, 1. This is a coordinate, it's not an interval. And in my x-intercepts, as we said before in our range, we never touch the x-axis, so there is none, not applicable. And finally, an asymptote. Do we have an asymptote here? Yes, we get really, really close to 0, so y equals 0 is our asymptote. Now, why do we go over this? Because what we're going to learn now is the inverse of exponential functions. So to inverse this, let me actually just, a quick reminder, inverses with, let's say we have a g of x equals f, the inverse of f of x. So this, actually we want to keep this in sight. If it's the inverse, I want all the coordinates to be flipped. So over here I had 1, 2, I had 2, 4, I had 0, 1. And I had over here, let's say I had -2, 1/4. All the x and value values switch for inverses. So I have 0, 1, I now have 1, 0. I have 2, 1. I have 4, 2. And then these also get smaller. And that is my g of x, or my inverse of f of x. And we'll see over here, my domain, if my x and y values swap, my domain is now my range. So it must go from 0 to infinity. And we see we get really, really close to 0 on our graph. My range is now, I could go to -infinity, I go to positive infinity. So it's all real numbers. My y-intercept is not applicable because we no longer touch it. And my x-intercept is now not 0, 1, it's now 1, 0. And finally we have an asymptote at x equals 0, so the y-axis. Now what's the whole point of this? So we had to learn exponential functions, we had to learn inverses, to now learn what is now the inverse of exponential functions. So this graph right here is actually a logarithmic graph. Logarithm up here. So a logarithm is the inverse of an exponential. So let's say we have an exponential b to the a power equals c. My independent variable, going back up over here, we saw that we have 2x. The x is at the exponent, and my dependent variable, my f of x, is across the equal sign. So my independent variable, my a, results in my c. The inverse, I can't just swap these values. I need like undo this exponential. And there's no undoing this exponential. Square root only applies if this is 2, if my exponent is 2. In this case, it could be 2. It could be anything. It varies. It is 2 at times. We see over here 2 to 4. But when it's 1, what do I do? When it's 0, what do I do? I can't square root it. So this is where a logarithm comes in. Logarithm. So if I have b base to the a exponent equals c, that is equivalent to log of base b of c equals a. The base stays there, and we see we now have the base applied to c, and we get a. My independent variable and my dependent variable swapped places, where c is being applied, and I get a. This is true always. Let's take a little example so we can figure it out. So I have 2 cubed equals 8. That's given. We should notice 2 times 2 times 2 equals 8. As I do this, and as you do it, for the first couple times, I want you to always label it. B, A, C. So that I could look back at my formula sheet and I see, oh, log base b of c gives me a. Log base 2 of 8 equals 3. It looks like a bunch of gibberish, but think of log similar to sine, cosine, tangent. Is like just a function being applied to it. It's a bunch of letters, but log will just always be there. But let's try to make sense of it. So here I have 3 2's are being multiplied to give me 8. We know we have 3 2's. We're going to find out how much we get, and we get 8. But over here, I have 2 and 8, and I find out a 3 somehow. So the way that we like to describe it is how many of the base, so 2's, multiply to get 8. And this works for the first couple examples, but once we get to values that are where the result, where the 3 over here, my a, is not a clean number, let's say like 1.5 or 1/2 or -4, that kind of makes this kind of break apart. But for the first couple bits, that's just what we want to see it as. How many of the base multiply to get 8? I need 3 2s to multiply to get 8. And that's my answer right here. Now let's move on to the next little bit. Let's do another question, like what is this useful for? Log of 6 of 36. I want to evaluate this. Evaluate means you're given an expression and you want to solve for a value. You want to simplify it as much as possible. AKA, what does this equal? That's similar to saying if I had 3 plus 5 and evaluate this, we know that's 8. Over here, we have something right here. I want to evaluate this. To evaluate it, we label it B, C, and A. We don't know our A. I go over here, I see base to the a power equals C. 6 to a placeholder, we'll put A equals 36. And we'll see what is A? A has to be 2. So how many 6's multiply to 36? I need 2 6's to multiply to get 36. Let's now switch it up and see that this formula, this relationship between BAC equals log BCA. Oh, I forgot to say something. I'll write it down. In order to express this and express like logs, like this log right here. I've been saying it over and over, but we see log base B. So log base 2 of 8 equals 3. That's how we write it. Log base 2, it is the base, similar to exponents. So log base 2 of 8 equals 3. That is how we say it. Log base B of C equals A. Log base 6 of 36 equals 2. We'll see that this is very flexible, this little relationship. Log. So that's kind of it for today. We're going to go over a lot of example problems. So skim through, see whichever example problems you want to work on. So log base 4, and this is all evaluate for now, of 16 equals what? I want to evaluate this. So I label it B, C, and A. And my formula I'll write over here is B to the A power equals C. 4 to the A power equals 1 over 16. I see over here, I have it's 1 over something, so I know it must be negative. A must be negative. And how do I get 16? I need to square it. So 4 squared is 16, and I see it must be negative. So A must be negative 2. At this point, we're doing this because it's really hard to kind of solve for A mathematically. There is ways to, but that's not in the scope of pretty much any class I've taken, even up to like Calc 4. So what we do is kind of just observe and see how can I get 16. We split into different pieces. How can I get 36? 36 we should know. Some cubes we should know. But when it gets to something like this, we could always like plug in. We could plug in and be like, oh, negative 2, it should be negative. So this is negative 2. That's my answer. Next up. Log base 17 of 1 equals what? Evaluate this. So B, C, and an A. 17 to the A power equals 1. How do we get to the first power? How do we get something to equal 1 to some power? This is a rule that we had all the way back up here, where to get the output of 1, we need input of 0. And that is a rule for all exponents. Anything to the 0 power is 1. We need 0 17s to get 1. So a will be 0. Let's do a nice little fun one. Log base 9 of 3. B, C equals a. 9 to the a power equals 3. How do I get from 9 to 3 in terms of exponents? And a quick little reminder, exponents are actually not the other way around. Square roots, roots, cube roots, all that stuff, those are exponents. Square root of 9 equals 3. Square root is equivalent to the 1/2 power. I need half of a 9 to get 3. Or like, not really. Like splitting a 9 in half in terms of multiplication. So I'm going to split it into two equal parts that multiply to get 9. So I split it into 3 and 3, and those multiply to get 9. I'm splitting it in half, but multiplication-wise. So 9 to the 1/2 power equals 3. So therefore, a is 1/2. 1/2 would be my answer. Just like with cube root that's to the 1/3 power. Fourth root of x is x to the 1/4 power. Those are some little recap that we want to go. So what we're doing is we've always been doing a is unknown. So now let's move on to when b and c might be unknown. Log of base x of 25 equals 2. In this case, it will be solve for the variable or the missing variable. We still label it b, c, and a. X squared equals 25. And now here, we can either see that's 5, or I could square root. And as I square root it, what squared is 25? You might have said 5, but also negative 5. They are both here. But one quick thing I didn't say above, I'll say in the next lesson with all the properties, is the base always has to be positive. It could be a fraction, but it always has to be positive. So we just reject this, and x equals 5. Log base x of square root of e equals 1/2. B, c, and a. So x to the 1/2 power equals square root of e. We learned before that e, and like the 1/2 power is square root. So x to the 1/2 power equals e to the 1/2 power. And this, we can get rid of the exponents, so x equals e. We'll learn about e next class as well. So now we did it when b is unknown. So let's try it. Log base 5 of x equals 4. B, c, a. 5 to the 4th equals x. And our calculators could solve this. So for this one, our calculators could solve it like x to any power. We could just do this square root, cube root, 4th root. Even if it's 1/2, we could just, our calculators can say like to the 1/2 root, which would just be square, but we can do it. This can also be done with calculator. The only problem is up here, these can't quite be done with our calculator. We could guess and check, we could see it, but we just need to understand these rules, where if it's 1 over, or if it's just a fraction. If it's a fraction, it must be pretty close to negative. If it's 1, it must be 0. This square root is 1/2, cube root 1/3. This one has a lot more rules. This, I believe, is 625. 625 equals x. 4 5s being multiplied together gives me 625. Now all this concluded in the end of our homework with these type of questions. 2 plus log, I'm just gonna make actually I have it right here. Log base 2 of k equals 4. Now my formula above, log base b of c equals a, I need it to look exactly like this. And you see I have this plus 2. That's kind of preventing me from doing it. I can't just ignore it and be like, oh, I only want this. We can't do that. We have to look at the entire problem. I can't exclude it, especially if I'm crossing the equal sign. If I wasn't crossing the equal sign, I can do it. But here I am crossing the equal sign. So I must get rid of this plus 2. And that, how do you get rid of addition? Subtraction. Log base 2 of k now equals 2. We do our b, c, a. 2 squared equals k. So k equals 4. Nice. And the last type of question that we'll go over is -5 times log 3 of x equals 10. There is a way to solve this in the future, but for now, we want to stick with these rules and be like, I want to get rid of this -5 because it's still being multiplied and I still don't like that. So I must divide by -5. Divide by -5. Log base 3 of x equals -2. B, c, and a. To get 3 to -2 power equals x. Or x equals 1/9. So the homework that was assigned is filled with problems like these. Feel free to do them. This is pretty fundamental. You want to really get comfortable at switching between log to exponents. And also we'll touch on a bit switching from exponents to logs, because there are times when we don't know the exponents, so we want to switch it to log. Okay, like 2 to the x power equals 10. 2 to what power is 10? I have no idea, because when we do with power, 2, 4, 8, 16, this is 1, 2, to the third power, to the fourth power. I see in between 3 and 4, it becomes 10. I can't just guess, oh, it's 3.2. That does not work. I can't be like, oh, x is 3.2. To mathematically solve for it, I need to switch it from b, a, c to get log base 2 of 10 equals x. And we could either leave our answer like this or use a more advanced calculator to find exactly how to find log base 2 of 10. So that is a glimpse into the future. There's much more to do with logs, but logs overall is not really confusing. It is just a lot of new formulas and new interactions, and conceptually it kind of falls apart once you go beyond whole numbers, whole positive integers. So this is a good start. I want to build a good foundation so that we can do more stuff with logs without feeling too overwhelmed. Thank you.